Hey guys, it's Eric. Welcome to my fourth year, first semester final project on VFDs in the workplace. I do want to throw a quick disclaimer out there for anybody that happens to find this public video on YouTube. This is meant as an assignment, not necessarily as an instructional piece. So just keep that in mind. If you decide to keep watching, it may not be the most informative thing you've ever seen. There are certainly better videos out there on YouTube talking about this subject. All right, guys, let's jump right into it. So let's start off with why are VFDs so important to learn about and to understand. It's really because they've become a cornerstone of our industry, and we're going to encounter them every day. And it's important to understand how they work, how they function, so that they do what we want them to do and do them in the most efficient way that they can to really give us the best chance of success in the field on a daily basis. So what are we going to be covering today? We're going to cover what is a VFD, variable frequency drive is what that's abbreviated for. I really want to go over how they work. I think that's going to help us understand what they're doing. And thankfully, the recent labs we've had should really help us understand at least the first portion of it. And then what are the advantages to it? Like we don't necessarily just want to do something for the sake of doing it. So why are we doing this? Why are they becoming so prevalent? And why are they going to stick around for a very long time? All right, let's answer the simplest question. What is a VFD? We just said it in the previous slide. VFD stands for variable frequency drive. Now, what is that? A VFD is really an all-in-one motor controller. It allows you to do everything from controlling how your motor stops and starts, make sure all that's nice and smooth, to being able to sense different things like overloads, overcurrents, stuff that's important for like the health of our motor. We're able to see that. And it's able to give us some at least can give us like real-time data in terms of like the hertz or the amperage that we're pulling while a motor is running, which can be useful like if you're having a troubleshooting issue or you need to make sure that like everything is functioning the way that it's supposed to. VFDs are very helpful in a lot of ways, just in a visual sense. Let's answer the real meat and potatoes question about this presentation, which is how does a VFD work? So we have three main parts. We have our rectifier circuit right here. We have our DC bus. We have our inverter. So this right here, full wave rectifier. This is exactly what we're doing in class on Monday. We're in the last class we had before this presentation. So what we're going to be doing is we're going to be bringing our three-phase in here, converting it into DC. Right here, this DC bus has a capacitor on it. We're going to use this capacitor to filter that and make it a nicer, smoother signal. And right here, this section right here, our inverter, is going to turn it into a simulated AC signal that we can use to then power this motor. We're going to get into a little bit more detail on that, but that's the gist of what we're doing right now. For our first step of our VFD, we're going to talk about the rectifier. So we're going to start three-phase AC signal right here. Here's our rectifier circuit. So you'll notice that I wish this GIF was a little bit slower, but basically this is just our phase going through its standard cycle. So we're going to be switching these ones down here to change our return path. So let's say A is active, we'll use this one as A. As A comes up like this, our B phase is being used as our return path. But then as A over here then comes down, we're going to be using C. And that allows this to move and not allow current back and like short it out. But then like as B would be active, C would start off as being the active return path, and then as B was on its downward side of its sine wave, we're going to switch over to A. And then, okay, so now A is active here, B is active here, B stays active, so on and so forth. Here we go with step two. This is our DC bus. So once again, let's think back to the lab that we did on Monday. So this is a full wave rectified DC signal. So we've accomplished what we want to do with our rectifier, but now we need to use something to make it like a workable DC signal, something that's nice and smooth. So what we're going to do is we're going to add a capacitor to our DC bus. So this is what it looked like when we had just the two diodes in the lab. So how do we get this to be nice and flat like this? So what we're going to do is we're going to charge that capacitor on the rising side. And we're going to discharge it as it falls. And that's going to give you this nice little sine wave. And yeah, it's not perfect, but it's usable. It's more usable than this would have been for what we want to do. And I should have a better example of that, of how we get to this from this on the next slide. So yep, here we go. This is a nice example of what I was just talking about. Just to go through it quick, so we're going to be charging as we come up on the rising side, and we're going to discharge our capacitor right here to help keep our voltage at this level as opposed to letting it drop all the way down here. So this is what's going to give us that nice DC ripple that we can actually use. Now that we've rectified our three-phase coming in into DC, and we've sent it through a filter to give us a nice smooth DC signal, what are we going to do with it? How can we make this work for us? That's where the inverter comes into play. So the inverter is a set of transistors, IGBTs. Long form would be insulated gate bipolar transistors, and we're going to be using these switches, and we're going to be pulsing them to simulate our three-phase that we can then use on our motor. So do I have my laser pointer up? I do not. Hold on. So if we're looking at this, these are our transistors, and these are what we'll be using to switch and control the speed and the torque of our motor as we go forward. So how does our inverter use those IGBTs to give us our simulated AC? So if you look at this diagram right here, so what we're doing is, and this is a constant right here, this is actually a representation of time. So this is telling us how long our switches are closed for. So this would be our shortest amount of time, and as we want our sine wave to rise, we leave the switches closed a little bit longer and a little bit longer and a little bit longer till we reach a peak, and then we're going to close them faster and faster to bring it back down. This is pulse width modulation right here. I'm kind of a slide ahead of where I want to be, but our pulse width modulation is what's giving us our frequency. And then that's what's going to be usable for us when we apply that to our motor. Here we just have a slightly different graphic showing that inverter and what those IGBTs are really doing. So this is where you're actually, your frequency is getting controlled on your output. So this is kind of the end of how they work. So at this point, we've gone all the way through the rectifier. DC buses is smoothed everything out, and now we have everything leaving on our outputs. So let's move on to our next topic. All right, so our final topic is going to be the advantages of VFDs. We already touched on one of they serve a multi-purpose role within our motor circuit. They contribute pretty decently to cost-saving factors wherever you end up having to put them in, and the wear on equipment is usually reduced whenever you put a VFD in. VFDs do a really good job of taking your motor circuit and condensing it down. So you're gonna eliminate your motor starters, you can eliminate overloads, and you can eliminate soft starts. And all of that is really going to reduce the footprint of your motor circuit. Not that freeing up space in a cabinet that's already there really matters, but in a new installation, you can reduce the size of your enclosures quite a bit when you don't have to have all these multiple things that one piece of equipment can serve that function for. Cost savings with the drive comes in a couple of different ways. You're not going to see it right away. It's definitely a long-term thing. But one of the things that you'll see that's a little bit, it's less tangible, but it makes a difference, is when we can lower the inrush current on our motor, we're going to be reducing our draw on the utility, which is going to reduce the amount we actually have to pay to power our facility. That would be like, that's the less tangible. You're not going to see that every day. We're not going to experience that so much. But the other side to cost savings is swapping out older DC systems for newer AC systems. I do this on a regular basis at work where I have to replace a DC drive and a DC motor on a conveyor. We do it as they die, um, but you're going to end up saving yourself the maintenance cost of going out and having to preventatively maintain a DC motor and have to check on brushes, and it's just one less thing you have to worry about with an AC motor. So piggybacking off of the previous one, talking about cost reduction, we can really, this is like a cost reduction part two. We're reducing the wear and tear on all of our equipment, electrical or not, by allowing it to operate smoother. So if you think about it and you have these ramp stop and start parameters, you're reducing the amount of wear that you're going to put onto your belts and your sprockets and your chains whenever we're trying to drive, because we're allowing things to just be smoother. All right, boys. This is the last slide. Just a summary of what we talked about. A couple Kahoot answers are going to be on here. Other than that, I'm over my 10-minute mark. Everybody, good luck on your final.